All right, what's going on, everybody? Today we're doing another LeetCode video. This problem is called same tree. So we're given the roots of two binary trees, P and Q, and they want us to write a function just to check if the trees are the same. If they're the same, we can return true. If they're not the same, we'll return false. And by the same, they mean structurally identical, and then also all of the nodes have to have the corresponding nodes have to have the same values. So for this first example, we can see that trees P and Q here on the left and right are exactly the same, both in structure and in the value of each of the nodes. So the output there is going to be true. So example 2 gives an example of two trees P and Q that are structurally different. So while the nodes look like they're the same, they don't have the same structure. So tree P here has a left child node, and tree Q here does not have a left child node. So again, structurally, they're different, so we return false. And for this third example, we have an example of two trees who are structurally the same, but their nodes do not all have the same corresponding values. So just to take an example here, this left child node has a value 2 for tree P, but tree Q, the left child node, has a value of 1, right? And 2 is not the same as 1. So these nodes don't have the corresponding values, so we return false. So that's pretty much it for the examples they give us. Let's go ahead and whiteboard. Let's whiteboard an example just to kind of see how this algorithm is going to play out. I'm going to implement a depth first search. So it's going to be recursive depth first search. So on the right here, this is basically the pseudocode for our algorithm. So there's a lot of ways you can actually implement this, I noticed, just in order of the conditions, but I found this approach to be one of the most concise and easy approaches to understand. So let's just go through it. So the first condition we're going to check, basically, by the way, at each recursive call, we're going to have just be comparing two nodes that correspond from our binary trees P and Q. So we're gonna look and first check if, for our base case, to see if they're both not null, or if they're both null, sorry. So, and if they're both null, we know we're at, basically, we've exhausted all of the nodes in the search path. So, and if we've gotten that far, we can assume everything above it has been true. So we can safely return true there once we get to the bottom. Okay, for the second comparison, we're gonna see if we know that it's not possible that both of them are null, we need to see if one of them is null, because if one of them is null and the other one isn't, that's a problem. That's a structural difference, right? So we return false in that case. That's another base case. So otherwise, if there are two nodes there and we know we can safely compare the values of those nodes at that point. So we're going to actually do recursion. So we're going to do recursion on the left and right subtrees for both trees. And we basically want to see if the recursion comes up as true for both of those. And if it does, then we can return true there. Otherwise, we're just going to return false, because the only way it can be true if there's nodes there is if their values are the same, and if all of the subtrees recursive calls have the same values, right? So that's pretty much it for a concise, recursive depth first search implementation here. Let's walk through this. So at first, we'd enter our recursion from the root node. We can see that there are indeed two nodes here, so we'd be down here at step 3. We need to check the values. The values are the same, so let's do recursion on the left child node of P and the left child node of Q. All right, so we can see that there are indeed two nodes here and the values are the same. So let's do recursion again. And now we're at the base case, right? We have two null pointers here. So we can return true and we can pop back up. to our 2. So at this point, we can search to the right, and we've reached the base case. Again, we have 2 null nodes here, and for P and Q corresponding, so that's going to be true in the return value, and we can pop back up. So at this point, we'll be back at the recursive call for this these nodes labeled as 2, and we can see that the function calls both came up as true, so we can return true here because both of the subtrees were the same. So we're going to pop back up now to the 1, and we can start searching to the right. So now we need to go to the left, because we always go to the left when we can for this implementation, just because that line of code is going to come first. So we're going to go down to the left. This is going to be true, 2 corresponding null pointers. Okay, so we're going to pop back up to our 3, and now we have to search to the right. All right, but as we can see, one of these nodes is null, and the other one has a node here. So we can't even compare the values. We know this is structurally different. It's going to be this line. So this is going to return false. And at that point, we don't even get to the recursive line. We're done exploring the trees because we've found a structural difference. We know they cannot be the same at this point. So we're just going to backtrack all the way back up with false, because we're going to compare. Both of these subtrees need to be the same. It's going to be an and comparison, and it's not true, so it's false. We can pop back up. Again, both of these need to be true. They're not both true. One of them is false. So we're going to have a false, and that's going to be the return value. Okay, so that's pretty much it for stepping through an example where these trees are different. In terms of the time complexity, so the time complexity for this algorithm, we just saw that we have to visit every node once. So we also have to visit the null pointer nodes of the leaf nodes, or if there's just a left child or right child doesn't exist, we've got to visit those null pointer nodes. But either way, the time complexity is going to scale with respect to the size of the total number of nodes of whichever tree has less nodes between P and Q. So it would be like the minimum of M and N, if you called M and N the size or the number of nodes in both trees. But I'll just say big O of N, and we know that N, I just defined N as being the number of nodes in the smaller tree. So big O of N, linear, and then the space is going to be and then, you know what, let me actually, so just to avoid oversimplifying this, it's going to be the minimum between M and N, right? That's like kind of what I was discussing. So the smaller of the total number of nodes of between P and Q. And then space complexity will be big O of H, because even though it doesn't appear like we're using any data structures, the recursive call stack actually grows linearly with the height of the tree. Because notice when we first started iterating, we went all the way down to this null pointer here, which is scales, that would scale imaginably corresponding to the height of the tree we had, right? It could even be big O of N, depending how you look at it, because if their tree was like really skewed, the total number of nodes in the smaller tree could be just super skewed one direction, giving you big O of N. So however you want to look at that, big O of H, really probably on average, if you don't have very skewed trees. So that's the time and space complexity. Let's get into the code. So we kind of had pseudocode, so we've already seen this kind of a little bit basically, but so if not P and not Q, we know we're at that null pointer. Everything to that point has been true, so we can return true. Let me wrap this in curly braces. Don't really need to, but I like doing that. So if not P and not Q, we return true. Then we need to see if only one of those nodes is null. So if not P or not Q, then we're gonna return false, right? Because that's a structural difference right there. At that point, we know both of the corresponding nodes are not null, so we can compare their values. So we want to check if the value for P is exactly equal to the value for Q. If they're exactly the same, then we just want to go into our recursion. And actually, we can kind of do this as a, we can probably do this all in one line. So let's do our recursion in one line. So if those are the same, and by the way, it would evaluate this first, so it would never do our recursion if these weren't the same. So this is why this kind of works here. So if those are the same, then we can keep evaluating these conditions. We'll go to the right and we'll say, okay, is same tree on those left children of P and Q, so left, Q left, and is same tree. We have a third, so it's gonna get pretty long, but I do think it's kind of nicer not to have a bunch of nested ifs here. So if it's also the same tree on P right and Q right, then we can return true, right? We know that they're exactly the same at this point, because when this part of the code is running, like once we get here pretty much, because this is going to be recursive, it's going to do all of this first, but this is pretty much, this line is basically like when we're backtracking up from our recursion, so we're going to keep returning true or false, right? Return false if those two values there, so if this value and this value don't come back with true, we need to return false. Or if the values aren't the same, we'll return false. So that's pretty much it for the code. Let's go ahead and run this. But hopefully this video helped you understand the problem more. If it did, leave a like and subscribe, and I'll see you guys in the next video. Peace.